Hi, it's Mr. Anderson, and this is Chemistry Essentials, video 22. It's on Lewis diagrams and VSEPR models. And it's a powerful model if we can use these two together to make predictions about the structure of something like methane over here. Works great if we're looking at atoms that are bonded covalently and also in ions. And so we could take methane, for example, look at its constituent parts, so carbon and hydrogen. We could figure out their Lewis dot diagrams. If you don't know how to do that, I'll put a little video up here so you can see that. Then you could create a Lewis structure, and finally we can create a VSEPR model. And once we have that, we can learn all of these things about a molecule such as methane. And so it works on molecules. We start with Lewis diagrams, and I'll give you a method for drawing Lewis diagrams. What we can do is compare different diagrams that we come up with by looking at their formal charges. We can look alternatives, and lots of times we'll find multiple alternatives, and then we have to show resonance. Another model is to use a VSEPR model. VSEPR model is simply looking at where the pairs of electrons are, and they're going to repel each other. This is simply going to be Coulomb's law. And so based on that repulsion, we can create these three-dimensional models of what those Lewis diagrams look like. And so these two together is a pretty powerful model that you can use in chemistry. What we can use that to predict geometry, bond angles, bond energy, bond length, and we can even predict polarity based on that as well. Lots of times we're going to have to extend it. It's just a model. It's not actually what the atoms look like, and so we can do extensions on this based on overlap of bonds, and also sometimes it's confusing when we get odd valence electrons. And so I'll present another theory. It's called molecular orbital theory. Won't go into detail, but I'll kind of explain where that would be useful. And so first thing we have to do is to know how to draw Lewis structures. There's lots of different methods on how to do this out there. I couldn't find any good mnemonic devices. And so we're going to use VSEPR twice. VSEPR is going to be our model of repulsion, but it's also an easy way to remember how you draw Lewis structures. And so if we're drawing the Lewis structure, the first thing you want to do is add up all of the valence electrons. Next thing you want to do is just sketch out the skeleton of where the atoms might be connected. Next, you're going to add the electrons. In general, you should add it to the most electronegative atoms first and kind of work from the outside to the inside. After you've done that, we can look for pairs of bonds, and then finally we're going to review the formal charges. Now, I know this seems confusing, but we'll work through a number of different molecules, and I think it'll make sense. So let's say we're starting with this. This is hydrogen cyanide. If we're going to draw the Lewis structure of it, the first thing we want to do is draw and add up the total number of valence electrons. So to figure out valence electrons, we're ignoring the metals. You can see I've removed that D block right here. But what we've got is if you're in this first column, then you're going to have one valence electron, so hydrogen. If you're beryllium, you're going to have 2. If you're carbon, you're going to have 4. And so we go up to this molecule and we're going to add up all the valence electrons. And so that's 1 plus 4 plus 5 is 10. So we start by adding the valence electron. Next thing we do is simply sketch out the skeleton. An easy way to do that is to just sketch it out by drawing bonds between each of the atoms as they are in the molecule itself. And so we've done that. Now, since these are pairs of electrons, we had to remove 4 of those electrons, so now we're down to 6. Next thing we do is we're going to add the electrons. And so we should add that to the most electronegative, or generally the one on the outside of the molecule. We'll get to carbon in a second. So I'm going to add that to satisfy the octet rule. Remember, nitrogen wants 8 electrons. So it's going to have 2, 4, 6, and then it's sharing the 1, so it's going to have 2 electrons here. So nitrogen at this point is totally happy. But you should see that carbon's not so happy. And so now we go to P. We're going to look for pairs of bonds to try to make carbon a little bit happier. So what we could do is we could share one of those electrons from nitrogen, or one of those pairs, and now nitrogen still satisfies the octet rule, but carbon's closer. Now it has 6 around it. And so we could try that again, and now we've got a Lewis structure for hydrogen cyanide. What's the last thing we're going to do is review the formal charges. And a lot of people don't know what a formal charge is, so we're going to start and go across from the left to the right with hydrogen. How many electrons does hydrogen have? How many valence electrons does it have? Well, it has 1. How many have I assigned it in this model? Well, I've assigned it 1 electron. Remember, it's sharing one of its electrons with carbon, but one of the electrons is really it. And so we're going to have the 1 valence electron it has minus the 1 assigned, and so it's going to have a formal charge of 0. Let's go to carbon. How many valence electrons? It's going to have 4. How many is it sharing? Well, it's sharing 1 here, 1 here, 1 here, 1 here, so it's sharing 4, so it also has a formal charge of 0. Let's go to nitrogen. Nitrogen has 5 valence electrons. It's got these 2 just to itself, but it's also sharing these 3 over here, so it's got a formal charge of 0. If I got formal charges of 0 all the way across, I'm happy. That means that I've got a pretty good model. So let's go on to another one. Let's look at carbon dioxide. What do I do first? I'm going to add up the valence electrons. So that's 4 for carbon plus 6 for each of the oxygen. So I get 16. Now I'm going to sketch out the skeletons. So this is a quick tip that'll help you. If you have an atom written by itself and then a number of other atoms after that, generally this one's going to be in the middle. And so when I sketch out the skeleton, it's going to look like that with the carbon in the middle. Remember, I've used 4 of my electrons, so now I'm back to 12 valence electrons. So I'm going to add electrons. I'm going to add them to the electronegative oxygen on the outside. So how many have I added? I've added all of my electrons. I'm back down to 0. But you can see that carbon's not happy. So what I can do is I can do that pair switching right here. And now I've got carbon. It looks happier at this point. Now, if we review the formal charges, let's go from left to the right. If we look at oxygen, oxygen is going to have 6. How many does it have? Well, you can see that it has 6 minus 1. So it's actually going to have a formal charge of -1. So that's kind of not a great sign on my model so far. If we look at carbon, it's 0. And if we look at oxygen, it's going to have a formal charge of +1 because 6 valence electrons minus 1, 2, 3, 4, 5. And so it's going to have +1. And so could you put together this model in a different way so that I would have lower formal charges? For sure. What I could do is I could switch and get a pair on one side. I could switch and get a pair on one side. And now I got formal charges of 0, 0, and 0. And so this is what it looks like. Now I should probably jimmy this a little bit. I should switch these pair of bonds over here and these over here, but this is pretty close. Now let's go to ozone, O3. So I'm going to add the valence electrons, sketch out the skeleton. Let me add those electrons. You can see I've got an extra one compared to when I did carbon dioxide. And so now, if we draw that, I've got one structure like this. Could draw my formal charges. So that's okay, but can you visualize this, that I could kind of invert it the other way? And I could also get those formal charges. Remember, formal charges, the closer they are to 0, the more stable kind of that structure is. But these ones have the exact same formal charges. And so what am I going to draw? I'm going to draw resonance. I'm going to draw this arrow in the middle, this two-way arrow, and that means that this structure or this structure are properly. So we have to show both of those structures. Now let's get to the VSEPR model. So VSEPR model is the valence shell electron pair repulsion. What does that mean? It's very simple. It simply means that when you have a pair of electrons, they have this negative charge and they're going to push on other pairs of electrons and they're going to push on themselves. And so think of it like a balloon. If you were to hold one balloon, it would look like this. But if I were to give you 2 balloons, they're going to move apart from each other if we hold it in the middle. And so that tells us what the electrons are going to do and therefore what the structure is going to be. So imagine if we have carbon dioxide like this, it's going to be the same where if these pair of electrons, these pair of electrons, your hand is kind of holding it in the middle. And so what shape, 3-dimensional shape, do we think it's going to have? It's going to have this kind of a shape. We call that linear. Linear is in a line. I know it doesn't look 3-dimensional, but it will get there in just a second. What's going to be the bond angle between the two? We call that 180 degrees. And this is a linear model. So you can see now how VSEPR allows us to start kind of visualizing these in 3 dimensionals. Or in 3 dimensions. One quick note, if you're doing organic chemistry, lots of times they'll call this SP hybridized at this point. I'm not going to go into what that means in AP Chem. It's not important, but it is important that you understand the terminology. Let's go to 3 electrons now, 3 pair of electrons. So we got 3 balloons. It's going to organize itself like this. What's something that looks like that? Maybe nitrate. And so if we're looking at nitrate like this, it's going to have the nitrogen in the middle, those electrons around the outside. And so this is going to be that VSEPR model. It's going to be trigonal planar. So it's going to have these 3 electrons coming out, or these 3 atoms coming out. It's going to be a 120-degree angle between the two. But it's also going to be flat at this point. Again, quick organic chemistry note, we call this sp2 hybridized. So again, we haven't got to this 3rd structure yet. We haven't got to this 3rd dimension, but we're quickly going to get there. Let's say we're looking at something like ozone. Ozone, you might think is going to be linear, but if you look at this pair of electrons out here, what kind of a structure are we going to get from ozone? We're going to get a bent kind of a structure. And now let's get to 4 pair of electrons. With 4 pair of electrons, methane is that example I gave you at the beginning. What's that going to look like? Well, if you hold 4 balloons in your hand, it's going to have this tetrahedral shape. The bond angle is going to be 109.5, and it's going to really rise out of the paper itself. We call this sp3 hybridized, and that's kind of where it ends. In AP Chem, your knowledge of all these bond angles and geometry, know that we can also have more pairs of electrons, and as we do, we get to what's called, let's say we're looking at PCl4, that's going to be trigonal bipyramidal, and so they're going to branch off like this. What you really have is a trigonal planar here in the middle, and then you're going to have a linear structure right down here through the middle. Why do we call it pyramidal? If I were to connect those with lines, you can see how we kind of have two pyramids on top of each other. Octahedral is when we're going to have 6 pair of electrons coming off. Again, bond angle, you don't have to know it, but you do have to know that we call this an octahedral at this point. And so what are some extensions? What are going to be some things that we have to build on this VSEPR model? Well, one thing we're going to have to do is understand that not all the bonds are going to be the same. Single bonds like this are going to be different than double bonds like this, and that's because the orbitals are going to start to overlap. And so in a single bond, what we have is called a sigma bond. Sigma bond is where they're sharing those electrons between the nuclei. But as we start to add more electrons that are being shared, what we're using is an overlap of orbitals, and so we get what are called pi bonds. And so pi bonds, so this would be a sigma bond and then a pi bond, or I could say this is a sigma and this is a pi bond. Those pi bonds, as we add them, are going to be less powerful, but they're also going to kind of lock the molecule in itself, so you get formation of isomers. Also, sometimes the math doesn't add up. In other words, we're going to have an odd number of electrons. So how do we add these pairs if we're adding one single electron? So nitrogen dioxide is actually going to have a Lewis structure like this, but it's going to have one single electron out here. So we call that a free radical. And so there are extensions, and so we can build a better model. It's called the molecular orbital model, or orbital theory. It's based on quantum theory and mathematics. It's just a different model, and we can answer a lot of these questions, but it's probably a little too intense and a little too sophisticated for AP Chem. And so again, did you learn the following to use Lewis geometry and VSEPR models to predict geometry, hybridization, polarity? If you did great. Try one on your own. Let's say I give you water. Could you draw the Lewis structure? Could you draw the VSEPR model? Watch out for those electrons, and I hope that was helpful.